Good afternoon, everyone. Welcome to this new Next Friday talk. Today, the speaker is Marco Venere, a PhD student here at NextHub, but currently in a visiting period at MIT. And he will talk about quantum computing. So you can go. Thanks for being here.
Thank you for the introduction, Leonardo. And hello, everybody. I hope that you can see my slides.
Yes.
Okay, thank you. So today I will introduce my work, which is Rock the QASBA, the Sparse Blossom Algorithm on FPGAs, which has been done in the NextLab group. And I'm also collaborating for this project with Beatrice Branchini, Davide Conficconi, Donatella Asciuto, and Marco Domenico Sant'Ambrogio. Just a few words on who I am. I'm a PhD student in Information Technology at Politecnico, currently visiting MIT, and specifically Professor Sung-Won Choi and Eri Zhou, to work on fault-tolerant quantum computing. My main research interests are related to quantum error correction, quantum circuit compilation, and more in general, also hardware design with FPGAs. And the intersection of FPGAs and quantum is the main topic of this talk, actually. Regarding my work experience, I have a research internship at AMD working on FPGAs and also a research internship at Invariant, which is a spin-out from the National University of Singapore Center for Quantum Technologies, where I worked mainly on quantum machine learning. And the topic of this talk, as I told you before, is mainly quantum computing. So just to introduce you to this topic this is a new paradigm of computation, where the unit of information is not the classical bit, which can only be a value between either 0 or 1, but is the qubit. And the qubit employs laws of quantum mechanics to achieve actually a superposition of 0 and 1, which means that we can have both 0 and 1 at the same time inside this unit of information. Now, in the last decades, we had a number of very important milestones that we achieved. Specifically, in 1994, Peter Shor introduced a novel quantum algorithm for factorizing integers in polynomial time. And this represented a breakthrough which showed the potential of quantum computing for cryptography, but also more in general for industry. And in 2019, so in the last years, Google first, then we also had USDC, showed some examples of quantum advantage in which a quantum computers can achieve a computational task in a few seconds, which would require billions of years on a classical computer instead. And if we look at what will happen in the future, IBM plans for 2030 to deploy the first device where the number of qubits that we can use from a logical algorithmic level is 1,000, which would be a very good number. Still not enough for Peter Shor's algorithm, which will require at least 1 million noisy qubits. In the IBM, we will have 1,000 logical qubits, where we're going through that way. And there is an issue. The main issue with quantum computers is noise, and noise affects computation. So in this picture on the left, you can see the representation of a qubit as a vector in a three-dimensional space. In particular, this is called the block sphere representation of qubit. Now, you can imagine the noise affects this qubit by slightly moving it inside the sphere in a way which is actually unpredictable. And this is an issue because we cannot really achieve reliable performance with quantum algorithm, because every time we perform any possible operation, which may be like a small computational operation or a readout operation, we will actually alter in an unpredictable way the information inside the quantum device. So what we aim to do is we aim to correct these errors, and we aim to correct these errors in real time. This is why quantum error correction has started as a research field in the last years. So to better understand from a high-level perspective what quantum correction is, imagine that you have two different things, a quantum computer on one side and a classical computer on the other side. On the quantum computer side, what you do is you employ an error correction scheme to represent your information. So here you can see a grid. This grid contains some black spots, and some green and blue spots. The black spots are actually data qubits, which hold information, while the others are parity qubits, which try to keep track of what kind of errors are occurring during computation. What we do at every round of this error correction process is we measure these parity qubits, and we get a bit string called syndrome. Now, this syndrome is fed to a classical computer, in particular to something called decoder. And this decoder will try to predict what's the most likely error occurring during computation based on the syndrome bit string that we received. Now, once that we have this kind of errors, what we can do is we can perform some corrective operations to undo the effects of the error. Now, this overall loop keeps on and keeps on going during the whole computation. But in order to achieve real-time performance, we have to respect some very tight timing constraints. For example, for superconducting architecture, we must stay in the order of 1 microsecond in order to achieve real-time performance. As you can imagine, this is really too constrained for current software. In particular, what happens is that as we want to increase the level of reliability, we need to employ more and more qubits. And so the decoder software execution time will increase as a function of how many qubits we employ in our error correction scheme. And therefore, what happens is that we go well beyond the 1 microsecond timescale, and thus we cannot succeed in respecting these tight timing constraints. Additionally, what we would like to do is also to integrate everything, every part of this error correction scheme on a hardware level. This is not only because we want to achieve real-time performance, but also because the control logic that actually manages a quantum computer workflow is mainly in hardware. And by using a CPU for software tasks, we will not only increase the latency, but make the overall workflow excessively complicated. So what we do what happens in current state of the art is that most of these decoder modules are based on software, and there are two different branches of decoders actually. The first one is an algorithmic decoder, in which basically we develop some specific data structures that represent the way errors are correlated to the syndrome that we measure. For example, we have the Sparse Blossom Algorithm, which does a graph task called minimum weight perfect matching to achieve some far accurate decoding performance. On the other side, we also have union find, which also does graph processing tasks, but it's less accurate yet with lower latency, which is better because we want to minimize latency, but at the same time, we also want good accuracy. So we need to find the right trade-off. Finally, there is the maximum likelihood estimator, which achieves the highest accuracy but at the expense of very high decoding time. In addition to the algorithmic decoders, we also have machine learning-based decoders. Now, this part of the state of the art is way less explored than algorithmic decoders, but it turns out that in the last few years, there have been some very interesting works on that, in which basically we use machine learning models like graph neural networks or convolutional neural networks to learn the correlation between errors and syndrome bits at runtime. For this work, what we will do is we will focus on algorithmic decodings because it's well established in the literature, and in particular on the Sparse Blossom algorithm because it represents the best trade-off in terms of accuracy and decoding time. Now, to better understand how the Sparse Blossom algorithm works, we need to understand what's the main data structure inside the algorithm, which is the detector error model. The detector error model is a graph. In this graph, we have some edges, which represent what kind of errors occur during computation. We are employing something called the circuit-level noise model, which basically means from a very high-level perspective that every time that we perform an operation to a qubit, we imagine that there is another operation which represents the error. And we model these operations based on the error probability. In jargon, that's called a depolarizing error channel with a given probability P that could happen after a Clifford operation, or also before doing a measurement, or after resetting a qubit. In addition to the edges of the graph, which are the errors, we also have nodes. These nodes represent detectors. So basically, every time that we do error correction, we measure disparity qubits to get a syndrome. Now, it turns out that the combination of these measurement bits is always deterministic when there is no noise, which means that basically, if no noise happens during computation, you know that this combination of bits will give you 0 as outcome, if you do XOR operation, for example. But in case noise happens, you will get a 1 instead. So these detectors actually detect that an error has occurred. They don't tell you directly what kind of errors has occurred, but they are correlated with the edges, which means that they are triggered by only specific kind of edges, which is represented well by the graph. So the graph captures this correlation between edges and nodes, so the correlation between the errors and these detectors. Now, in order to understand what errors are actually taking place during computation, we do something called minimum weight perfect matching, which is a graph algorithm. So the idea of this overall algorithm is basically the following. At runtime, we measure these measurement qubits, these parity qubits, and we get a bit string. And given this bit string, we see what are the detectors that actually value 1. So these are the trigger detectors. Now, inside the graph, this means that we have some nodes that have been triggered. We want to match these nodes, which means we want to create pairs, basically, of these nodes. And the way these nodes are actually matched will tell you what errors are taking place. So there is an algorithm in state of the art, which is the Edmonds algorithm for minimum weight perfect matching, which is basically a linear integer programming problem that is used to compute this matching. It is divided into a primal problem and a dual problem, which is like the jargon for integer linear programming. In the primal problem, you build alternating trees and you develop all the structures to find a matching. But the dual problem helps you identify an optimal solution, which is a minimum weight optimal solution. We are looking for a minimum weight because we're looking for the most likely errors. So the errors which have a higher probability to be executed. There is an issue with Edmonds' algorithm, which is it basically relies on Dijkstra, which is this graph algorithm to find the distance between all nodes, and in particular on all-to-all Dijkstra. So you have this graph, which is a considerable size, and you need to compute the shortest distance between all nodes inside this graph. This is computationally expensive, and this computational cost increases quadratic in time with respect to the number of nodes inside the graph, and also consumes memory. So the literature devised this Sparse Blossom Algorithm by Oscar Higgold and Greg Gidney, which basically try to compute only a subportion of the problem. Basically, you only consider the nodes that have been triggered, that you can see here in red, and you build regions on top of these nodes with the idea that you will only look at them and you will neglect the rest of the graph. In this way, you save execution time and you also save memory. The idea is that we are simplifying the problem. We are not requiring the resolution of Dijkstra for all-to-all shortest path distances. And now we have also a visual representation of this primal and dual problem. Because the primal problem will build these alternating trees data structure, as I will show you later. And the dual problem builds instead these regions. And based on when these regions collide, you will find a match. This approach turns out to be very effective because you have a scaling of the decoding time, which is a polynomial with the 1.17 power when the error probability is 0.1%. This is an interpolation, but they will tell you that this is a saving with respect to the quadratic execution time, which is very important as we want to achieve real-time performance. So the least decoding time we get, the better. Now, going in depth into the Sparse Blossom algorithm will take way more time than we have available here, but I just want to give you some key concepts based on the Sparse Blossom algorithm paper. So if you see this picture, we have the main objects involved in this computation, starting from left to right. So in left, you have this overall graph, which represents all the detectors that you have in your error correction scheme. And you can see this blue region. So at the center of the region, there is this star, which represents the detector that has been triggered because an error has occurred. And you build a region around it. And during time, this region will grow or will shrink based on the workflow of the algorithm. Now, going to the right, you can see these two regions, which are green. The idea is that they grow during time and they collide with each other. And once they collide, we can say that they are a match. So we freeze these regions, they cannot grow anymore. But the idea is that now we know what kind of errors have occurred because we find a minimum path between these two regions. And this path will tell us what errors are taking place. Now, as required by the algorithm, we have a number of regions which are interconnecting between them. We call this interconnection alternating tree. The idea is that when multiple alternating trees get in touch with each other, we find matches. And when we find matches, we find the solutions to our problem. Now, sometimes it happens that these interconnections create a loop called a blossom, and we consider a whole blossom as only one node. But at the end of the algorithm, when we want to actually verify all the matches taking place, we will decompose this blossom loop into the specific regions which compose it, and we will match all of them together to identify the errors that are taking place. Now, what are the contributions of our work with respect to the whole sparse blossom algorithm? Basically, we do software profiling of this algorithm to understand what's the execution time of the specific components as we increase the size of the detector graph. And then we devise a hardware architecture, which is called QASBA, which is prototyped on FPGAs and allow us to cover the whole decoding algorithm for real-time performance. We also devised an automation process, which I will describe later. But basically, the idea is that we want to enable quantum engineers who are not expert with FPGAs to use our solution. Okay, so let's start with the software profiling task. In the software profiling task, we use Valgrind, which is a well-known tool in state-of-the-art to verify the performance of software modules inside an algorithm. And we managed to see the different portion of execution time taken by the three main components of the algorithm. These components are the matcher, the fladder, and the tracker. Now, without going too much in depth, the matcher basically manages the flow of the minimum weight perfect matching. So basically, the idea that we have regions that grow and shrink, the fact that they collide, the fact that we have alternating trees, all these data structures which are built on top of the graph, they are managed by the matcher. On the other side, the fladder takes into account the underlying graph data structure. So every time that two regions may collide or not, the fladder checks on the graph whether the nodes that are inside the regions touch or not. So as you can imagine, this is a very computational intensive task in case the graph size increases. And that's why the fladder can keep up to 2/3 of the computation of the overall workflow. Finally, we have the tracker. The idea is that matcher and fladder need to communicate with each other, and their operations must be scheduled somehow. The tracker keeps that into account by generating events which are managed in a priority queue. In this way, you only consider the events which are relevant for your computation, and you keep processing them and discarding other events which are no more relevant based on the computation that you actually performed. And given the software profiling, we devised our hardware architecture, which is called, again, QASBA. So QASBA is an architecture supporting two different hardware instructions, which are the load instruction and the decode instruction. And now I will go through both of them. So in the load instruction, basically what we want to do is we want to set up our FPGA. Now, a very important thing to consider for these whole experiments is that we are considering only one logical qubit implemented as a group, as a patch of different physical qubits. And we want to describe to the FPGA how these qubits are interconnected and what's the detector graph, which represents this error correction scheme. So in this stage, we will generate the required data structure and upload them to the FPGA. We have two stages. The software host on the software CPU will actually generate the data structures that are required by the FPGA. We are calling them, we are receiving as input a parity check matrix and a false matrix, which are used to describe the error correction code. We are also receiving some further hyperparameters, and we are generating the data structure. And then the prefetching stage instead is on the FPGA, and it actually simply moves data from the host software to the internal memory on chip. This is also something important because we only use on-chip memory. We do not use external DRAM on board on the device in order to minimize latency by minimizing the number of clock cycles required to access external memories. Regarding instead the decoding structures, that's used the runtime to actually decode syndromes. So every time you measure disparity qubits, you generate a syndrome, and this syndrome goes to the decoding to this decoding stage. And we have three stages here. The first one is a setup stage in which we initialize our basic data structures that are dependent on the input, which basically means that every time you have a node which has been triggered somehow, you need to be the region on top of it. So you initialize the regions. Then you have the minimum weight perfect matching workflow that beats all the regions, makes them grow, shrink, collide, and creates all the alternating trees. And once this computation is completed, we have a shutter stage in which basically if we have blossoms, which are loops between these alternating trees, we decompose these blossoms and finally match all the regions together. Now, I'm going deeper into the MVPM module because this is the most important part of the architecture. Here, we basically implement in hardware the three components which are software and which are described in the software profiling. So the tracker, the fladder, and the matcher. In particular, in the fladder, what happens is that we receive an event from the tracker, from the priority queue inside the tracker, and based on the kind of event, we perform different computations. For example, we have a look at node event in which we actually have to look at the graph data structure and verify whether regions are colliding or not. And then we have a shrink event in which a region is shrinking, and what may happen is that the region disappears or a blossom decomposes. And that's also based on the activities of the fladder. Every time the fladder finishes, we also generate a message, and this message goes to the matcher. The matcher receives a message, and based on that, understands whether what happened inside the graph. So whether regions are hitting each other, or whether a region actually hit the boundary of the graph, or whether there has been a blossom which actually shattered. And given that, the matcher updates the minimum weight perfect matching workflow. Now, it's not easy to actually move from software to hardware, so you may wonder how this happens. Well, basically, in hardware design, what you have is, in our case, a high-level synthesis workflow in which you can use C and C++ to represent what the hardware looks like and what features it should implement. But you cannot use all the high-level software routines that you can find in the software baseline, which is, in our case, pi matching, which is a library implementing the Sparse Blossom. So, for example, what we wanted to do is we wanted to employ data level parallelism, which means that since we have distinct data structures acting on different portions of the graph, we can run these operations in parallel to minimize the latency. We do that by using hardware techniques such as loop unrolling and pipelining. Also, in the way in which we initialize data structures moving data from the host to the hardware is via data bursting, in which in this way we can minimize the number of clock cycles required to actually load the information. And we store this information on the LUTs and the BRAMs which are on chip. Finally, a very important issue is that since we are using graph algorithms, it's very easy from the software side to implement these algorithms recursively. In this way, you first start on the root of a tree, for example, and then you look at the subtrees from the left branch or the right branch. And this also happens, for example, also in the shattering, when you decompose a blossom into its children regions, which may be blossoms recursively. Now, this cannot happen in hardware, because in hardware you cannot really implement recursive operations. So what we did instead is we implemented push-down automata, which are a specific theoretical computer science model in which you have a stack, and you basically grow this stack every time that you perform a recursive call. So we actually emulate these recursive calls by building elements on top of each other onto a stack. Now, after looking at the hardware architecture, let's also see this automation process that I mentioned before. So basically, the issue is that these quantum engineers that actually want to use a quantum computer may not really be expert in FPGA programming, and we want to ease their work. So basically, we devised this automation process, which receives some high-level parameters, such as what's the target FPGA board they were using, and also some customization parameters related to the error correction scheme. And basically, our automation process employs the FPGA programming tool chains, completely hiding the complexity of these tools. So in our case, AMD Vitis and Vivado. And as outcome of this overall workflow, we have this bitstream, which is the file that will be uploaded onto the FPGA to set up the overall architecture. As customization parameters, we may have, for example, the code type, the distance of the code, which tells you how many errors you can actually decode, the graph weights and the edge merge strategy, which are further hyperparameters related to the Sparse Blossom algorithm. Now, we also made an experimental evaluation of this work. In our case, we employed three different data center scale FPGAs, which are the MD Xilinx Albeo U55C, U50, and U250, with a target kernel frequency of 300 MHz. Our host CPU is an AMD EPYC 7V13 with 64 cores and 512 GB of RAM. And our software comparison is made against our software baseline, which is pi matching, and also Fusion Blossom, which is another work which came out during our process of designing this architecture. Now, our experimental methodology considers as metrics the decoding time and the energy efficiency. Now, there is an issue, which is how do you compute the decoding time of an FPGA, which would be integrated into the hardware toolchain of a quantum computer? Well, the FPGA in our setup is simply connected to a CPU via PCI Express. But this means that you will lose a number of clock cycles just to move data from the CPU to the FPGA because of PCI Express. This is something that doesn't happen in the real world with quantum computers because you don't use PCI Express to move data from a quantum computer tool to the FPGA. What you have on a real-world quantum computer is you have a module that performs pulse control to actually manipulate the qubits, which is implemented in FPGA as well. And then this FPGA module will interact with your error correction module. And ideally, you can also have both modules on the same chip of the FPGA. So in that case, you don't really have to keep into account this communication latency. Therefore, what we do is we count in hardware the number of clock cycles required for decoding, and then we also keep into account the frequency of the FPGA, and in this way we can compute the decoding time. Regarding the energy efficiency, instead, we want to do is we also want to consider how efficient our solution is compared to the software baseline. And to do that, we need to measure the amount of power consumption of both the FPGA and the CPU that we are comparing against. For the FPGA, we employ the AMD Xilinx board utility, which allows you to keep track of the overall power consumption of the board. For the CPU, we use the CPU performance counters, which are based on CPU registers measured via Linux perf utility. And we basically compute the energy efficiency in the classical way, which is throughput divided by power, which is 1 divided by latency per power in our case. Okay, let's see how our solution scales if we try to increase the code distance, which means we're trying to support more and more qubits. Now, the code distance is like the most important parameter for an error correction code. As you increase the code distance, you increase your reliability, but you're also increasing the complexity of the error correction type, and because you're increasing the number of qubits required by the error correction workflow. Now, as you can see, there is a bottleneck which our solution achieves, which is the amount of VRAM that we require. This is due to the fact that in order to reduce latency, we employ all data structures on chip. We implement them on chip, and the amount of hardware required to implement this data structure is obviously limited. Therefore, we managed to synthesize code distances up to d equals 9. At that point, we reach a cap in our implementation. And regarding the performance of the decoding time, for low code distances, we are close to the 1 microsecond threshold which we need for real-time performance. We reach up to around 8 microseconds for d equals 9. Obviously, the decoding time, as you can see, does not only depend on the code distance, but also depends on the error probability. This is because minimum weight perfect matching is an algorithm whose decoding time really depends on how many errors are occurring in computation. and how many detector nodes have been triggered, as shown by your syndrome. Now, we also compare different error correction codes in order to understand what their performance look like. This is also thanks to the flexibility of our automation process. So thanks to our automation process, we can support the repetition code, the surface code on both rotated and unrotated memory, and also the toric code. And as you can see, performance slightly vary from one error correction code to the others. In our case here is for a distance equals to 5. And the reason for that is that different error correction codes require a different number of qubits, and therefore they require a different amount of detector graph size in general, which actually impacts the performance of the decoder. So as you can see, the faster decoder is the repetition, which is comparable also with the toric apparently, and the surface code and the rotated surface code are the ones that take more time. Specifically, the rotated is more efficient than the unrotated because it takes a less amount of qubits. And we can also see different performance based on the different devices that we're using. We are comparing the U55C, the U50, and the U250. And different devices achieve a different kernel frequency based on the optimization done by DMD Vivado toolchain. And therefore, in our case, the U55C outperformed all the others for all error probabilities. Regarding the comparison against the literature, we are up to 25 times faster than the pi matching software baseline, and we are comparable with the Fusion Blossom work. These comparable results are due to the fact that Fusion Blossom inherently achieves a parallelism feature inside, which is very relevant for our work. And instead comparing the energy efficiency results, we are 300 times more energy efficient than pi matching, and we are up to 100 times more energy efficient than Fusion Blossom. Which is also a very important metric since we want to keep the temperature of the quantum computer pretty low. We are in the order of the millikelvins. Therefore, we want a solution which actually does not dissipate a relevant amount of power in the environment in order to avoid thermal dispersion and increases in temperature, or also additional noise introduced during computation. This is why the energy efficiency metric is actually relevant for our case. So, in conclusion, what we did in this work is we profiled and accelerated the Sparse Blossom algorithm, and we also devised an automation process for bitstream generation, which achieves relevant speed up and energy efficiency compared to the software baseline. Obviously, what we want to do for the next steps is to actually keep minimizing the decoding time, and to do that, we want to improve the memory footprint of our solution, since it's the main bottleneck, but also achieve higher code distances. In addition, we also want to extend our support to the Ultrascale Plus RF-SOC, which is a kind of FPGA that enables digital to analog and analog to digital conversions and can be used for pulse control. It would be very important to actually test the complete toolchain in which you have the error correction kernel and the pulse control kernel on the same FPGA. Okay, so with this, I thank you all for your attention. My talk finishes here. I don't know if you have any questions. I'm available here or also via email to marco.venere@polyme.it. Thanks.
Thanks a lot, Marco, for your talk. Is there any question from the guest here?
Well, no, actually.
Okay, so I have one actually. So
Yes.
I was curious if you can tell a bit more details on the difference between algorithmic decoders and maybe machine learning techniques. So
Okay.
you can expand.
Okay, thank you. Yeah, thank you for the question. It's very important actually. So in the last years, we've seen a number of increasing machine learning decoder solutions, and it turns out they are actually very powerful in learning the correlation between the errors and the detector nodes at runtime by using a considerable size of training data. And in this way, you can achieve a decoder which actually scales pretty well with respect to the code distance. So this is like a very relevant research direction, because compared to algorithmic decoders where you have a fixed data structure which increases considerably as you increase the code distance, and therefore you have a relevant memory footprint. On the machine learning side, you instead have a more efficient implementation. And another things to consider is that the decoding time with a machine learning solution is actually pretty known because the structure of the machine learning model is fixed. On the other side, for the algorithmic decoder, decoding time really depends on how many errors you are getting during computation. So I would say that in the next years, we will need more and more exploration on the machine learning based solutions.
And just another curiosity, as I
Yes.
work mainly on graphs, is there also room for graph machine learning methods?
Yes, absolutely there is. Indeed, there are some specific kind of error correction codes which are called color codes. And these color codes are not really represented as a simple grid, as it happens in surface code, but as a graph. And this graph shows you how different portions of the error correction code interact with each other. Now, in the machine learning based solution, when you have a simple grid, what you can do is you can do convolutional neural network because each convolution stage actually keeps track of these correlations. They are very local in the graph. While for the graph codes, you cannot really use convolutional neural networks, but you can use graph neural networks, and these graph neural networks can actually learn these correlations between errors inside the graph. And they prove to be actually pretty effective.
Thanks a lot. I will have a look into that.
Thank you
So
for the question.
if there are any other questions, thanks everyone for participating in the talk. Thanks Marco, the speaker.
Thank you.
And we will meet next Friday with Francesco Panebianco, a computer security PhD student here at Nextdoor.
Okay, thank you again.
Okay, last question.
So actually,
Yes.
so I think that maybe the problem for machine learning approach is that the inference time is not fast enough. So I just want to ask you if the algorithm approach is actually faster also because the inference time of the machine learning approach is not faster enough, you know, of the solution. And so how can we actually, improve it?
Sorry again, I didn't hear very well the question. Could you like get closer to the microphone? Sorry. Or
I think the question was about the inference time of graph or convolutional methods. So
okay.
what's the difference between normal methods? Like
Yeah, so actually can we, when we would use a neural network if the inference time is not, you know, fast enough than the algorithmic version of the recorders.
Okay. So
Of the quantum computer.
okay, so thank you for the question. So regarding this latency required by this machine learning model, I will answer. Tell me if I haven't answered completely because maybe I missed some parts of the question. But if the question is what's the latency achieved by these machine learning models also compared to these algorithmic decoders, I would say that the latency, if I'm not wrong, I saw some papers in which it is in the order of tens to hundreds of microseconds. So there's still a lot of work to be improved. But I guess that the convenient part of using machine learning based decoders is that you can actually do inference on GPUs, and performance of GPUs is actually improving by order of magnitudes in the recent years. So you can actually train your model on the GPU, you can actually do the inference on the GPU, and then give data to whatever is required for performing pulse control. There are issues with respect to the training time instead, because you have to train these models, and the amount of data required to train a machine learning based decoder may be really non-trivial. It may grow also exponentially with respect to the code distance, which is something to keep into account. On the other side, the algorithmic decoder does not need any kind of training, which means that once that you deploy this data structure, which is the detector graph, you can readily use it. And this is something that you need to take into account into the time cost required by your solution. Regarding instead this machine learning based approach, For sure, it can get faster and faster in terms of decoding time because you have a fixed duration of the model inference, and you are in the order of tens, hundreds of microseconds. But you also need to consider that a GPU must be then integrated into the quantum computer hardware toolchain, and you have some communication latency between the GPU and the control logic, which may also increase the overall decoding time. I don't know if that answers the question or if you have any other doubts.
Yeah, actually, my next question would be about the GPU and how we can implement it on the quantum computer. So it answers me all of it.
Yeah, exactly.
Okay, so I think we're done. Thanks a lot for the speaker and the guest. So see
Thank
you
you.
next week with the next
Thank you again.
Bye. Have a good day.
Bye.